Back to my YouTube channel. Today we'll be dealing with we're still under strength of material in 6 stick cylinders, right? We've given this is question 1. Was an exam question paper. This is a steel hollow shaft, right? We're given question 1. Read as follow: a steel hollow shaft. You see, this is a hollow shaft. That means it's a shaft that has a hole like that. It's a hollow shaft. We are talking hollow shaft is like this. As you can see, it has internal and external time. Then there's a solid shaft. It has no. This one has the internal and the outer diameter. Hopefully you know the difference there. An outer diameter of 200 millimeter and an inside diameter of 150, as you can see. Then they say is shrunk onto another steel hollow shaft. Imagine you are strunking hollow shaft with another hollow shaft. You'll have 3 diameters like this, 1 2 3, which is will have some common diameter there. Hollow shaft hollow shaft with the inside diameter of 100 and the outside diameter of 150. Then we have axial force of 171,239 kilonewton is needed to push the 2 shaft apart. The length of each shaft is 200 millimeter. The coefficient of friction between the contact surface is 0.25. The Young modulus of elasticity is 200 gigapascal. So question 1 says calculate the contact pressure due to shrinkage. Okay, it's fine. We want that one already. We are given, isn't it? The pressure, we've given the force. That one, it's a minor question. Simply, it's pretty straightforward, easy, right? We know that the force is equals to what? Coefficient of friction multiplied by pi dl, whereby then we multiply by what? By our pressure there. Coefficient of friction we are given there, which is 0.25, given 0.25 multiplied by pi. The diameter, remember this must be common diameter. Common, as you can see, common diameter will be what? 150. Check, we have 150. Also here we have 150. So these are common. You see, it's appearing twice. It's common. It's the same there. Here 150. Here again there is 150. So this is common, guys. As you can see, 150 is the same as 0.15. When you divide by 1000 multiplied by the length, which was 200, this is the same as 0.2 multiplied by that pressure that we are looking for. Then the force we've been given. We've been given the force. Let me correct this a little bit to the others like this. Okay, it's fine. Then the force, it's here for 471,329 kilonewton. 471,239, yeah, kilonewton, right, if I'm not mistaken. It was for this like this, 239 times 10 to the power of what? Power of 3. This is kilonewton. You want P, you divide by this, both sides, right? You know the maths. You'll divide also by the same thing here. You know what you're supposed to do there. You know there, when you divide, that will cancel. You know what you're supposed to do. You're supposed to get that the pressure will be equals to 20 megapascal. Now what is this 20 megapascal? Remember this these are compound. When you are putting, we have put solid shaft, hollow shaft in another hollow shaft. We'll have 1 2 3. This is the shrinkage with them. This is fall under what? The shrinkage graph. We know we'll use our shrinkage graph. I've We have discussed about this shrinkage graph. You'll have this guy like this, like that. This is our this is our common diameter. This is the outer diameter. This is the D1, isn't it? Internal diameter. But remember, we have this form now. That form goes like that, goes like this. Then we have that goes like that. Then we have, yes, goes like that. Remember, this is our hook stress. Also, this is radial hook stress. Here we have 0 0. This side is positive, then negative. We know that, guys, our Cartesian plane. So remember, pressure, we've got pressure is equal to radial at the common what I've discussed about this at the common diameter, because here it is string the axial force needed to push the two shaft apart is the common, is the, I've discussed about that. If you have given this, if you take that from the force, this will be that pressure that will get the same as radial pressure at common diameter. And then where it's our common diameter, it is here. There it's our common diameter here, right? Here it's our common diameter there. So we had that common diameter. Okay, I can write this so that maybe you'll see this is 150 millimeter. This is simply 200 millimeter. That was 100 millimeter. So the stress here, we got it here. There, what was that value, which is, remember now is 20, but here will be what, minus 20 megapascal. Yes, it's positive, but supposed to be negative megapascal. Remember also here, remember when you're using the force we're using here, remember this D becomes a common diameter. Or let me write it so that you'll know, you'll see the force is coefficient of friction multiplied by pi multiplied by what, common diameter multiplied by the length multiplied by pressure. This pressure will be the way at the common diameter. Check there on your textbook, it is common diameter. So obviously this we are using common diameter. Obviously this pressure will be for the common, guys, and then there the common, it is here, will be radial. Okay, but it will be negative because this region is negative, right? It is negative, right? So I was just explaining there. Then 1.1 okay, sorry guys, 1.2 says the minimum hook stress induced in the what, inner shaft. Okay, inner shaft, take note, inner shaft. If you have given this graph, guys, this is the one and the same thing. This is simply compound. Remember, from here till there it's a inner. I said this is a part for inner. From here until there is a part for what, for the outer. It's either outer shield cylinder or it's the outer shaft, guys, if you are given two shafts that are strung together. So here we'll find A and B for this portion. Also we found A and B for the second portion. So I've discussed about this. So let us take our question. So what do we have there on the inner shaft? We know the stress here is 0. We have calculated that, so we can go 1 point, oh sorry about the highlight, let me check, 1.2. we know that. can say we're working where we're working. Obvious, the question we know that you are working at the linear. Remember, okay, but we can say, just for in case, linear, not diameter, linear shaft, or inner shaft. The at diameter, can say inner shaft. Now we're working at what? You tell the measurement at diameter d1, which is equals to 100 millimeter. This is the same as 0.1 meter. So we know there our radial stress is equal to 0 megapascal. From where here I've discussed about that. There, no, or I will try and change this. Let me use some different highlighter. There, you see, here is 20, negative 20. Also here we have 0, but now we're focusing on this part first for the in, right? So what it is, radial, we know that radial is given by a minus b over d squared. A we set is 0, a we don't know, minus b we don't know, diameter we know is 0.1, we square this, right? Then we make a the subtract. If you make a, therefore a will be equals, you take this to the other side, will be positive. You'll have this to be b over 0.1 squared. You can call this equation 1. Then we're done with this first path. Remember, this is only what we know, so we can come here. The common diameter can be the common diameter. Can also write, can even write it here. Can do like this. Can even write it here. There's nothing bad. And let me now add common diameter. By the diameter there is 150 millimeter, which is the same as 0.15 meter. Okay, what do we know? The radial there we've given is minus 20, the one that we've calculated, megapascal. What is radial stress? We know that radial stress is simply a minus b over d squared. Radial is minus 20 times 10 power 6. We don't know the value of a. B, I don't know. Diameter 0.15 squared is. This is simply just what? Equation. There's nothing we can do again here. Right. There. Can have this as equation 2. Then we know we can say substitute equation 1 into 2. You see where I see a, I will replace a with this whole thing here, as you can see there. Okay, it's fine. As I substitute that into 2, here we have minus 20 times 10 to the power of 6 is equals to a is b over 0.1 squared minus b over 0.15 squared. All right. So the matter of maths, I've been discussing about this. This is the same as 1 over 0.1 squared minus 1 over 0.15 squared. Right. Remember, you can take out b as a common factor if you want. The same is like that. Punch this, the value that we'll get there. What is the value? So yeah, I'll take my oh sorry, ish, I've just dropped my pen. Sorry guys, wait a little bit. 1 minute. All right. So let me do, we say 1 over 0.1, we square that, you minus this by 1 0.15, we square it. This will be same as minus 20 times 10 power 6, 5.556. Here we'll have what? B. Alright. Then we divide by this. We know the method of maths. So this will cancel. Therefore B will be what? If we punch that, let's punch this on our calculator. 20 times 10 to the power of what? Precisely 6. And 5.5, oh sorry, 55.556. This will be minus 359.99. I have 99 there. 7 times 10 to the power of 3. So to find A, we know that A, it was A here. Come and grabs our A and grab our A there, isn't it? This was A. Then now we know what we're supposed to do. A will be equal, when we see B, substitute B is that we've just calculated now, isn't it? Then alright, so let's go about it. Clip that, let's find the value of A. Minus 35 times minus 359.997 times 10 to the power of 6. Alright, positive 6 into 0.1, we square this guy. This is simply minus 3,5999, because this 997, this will round off, will same this, if we round off, will affect this and affect, will have 6. This is simply equals to 6, as you can see, times 10 to the power of what? Of 10. Okay, that is A. Now we have the value of A and B. Here we're supposed to calculate what? The minimum hoop stress induced at the inner shaft. Okay, the minimum hoop stress induced in a inner shaft, or minimum hook stress in the inner shaft. The minimum one, where it is, where are you going to find the minimum? It's here. We'll better common check this graph there is below what minimum. So they want what minimum, the minimum hoop stress induced in the initial. Okay, minimum will be here at 100. Okay, minimum, we suppose if we have a large diameter, we'll have a maximum. If we have a smaller diameter, we'll have a minimum. So the minimum is simply, if we have a small diameter, we'll have the maximum. If we have the bigger diameter, we'll have the minimum. So the minimum is here. there. The minimum is here, then the maximum will be here where we have the smaller diameter. So let the common diameter is 0.15. So okay, let's find the stress there. The hook stress, we know, can see the hook stress at 150 millimeter is A plus B over D squared. It's in it. A is minus 3,6 times 10 to the power of 10 plus what is B, negative 359,997 times 10 to the power of what, 6 or 3. Then this all over this 0.15 squared. Then we'll have minus 3,6 times 10 to the power of 10 plus minus 359,997 times 10 to the power of 3. Divide this by 0.15 squared. Alright, what will I have there? Let me check. Negative 3,602 times 10 to the power of what, of 10. Obvious this is Pascal, but let me divide this by what again. Let me just say engineering. Again, engineering, this must be, this is the same as minus 3,6,015 this, okay, because it's 999, this will be same as 6 megapascal. Can write this in megapascal. All right, this is what we have. Then what about the maximum hoop stress induced in the outer shaft? Maximum stress induced in the outer shaft. Now supposed to get again A and B. It's another thing here. Supposed to get A and B. Remember this, now it's the outer shaft. Supposed to get A and B from this position, from here till there. Remember this is the outer part. So A and B at that position. All right. What do we know at this point? We know the stress here, and then okay, we know the stress, and then the radial here, it is 0. Oh, fine. Then at the common diameter of 150 we come, you can say at the outer shaft, working from at common diameter, simply say DC, whereby that is 150 millimeter, is the same as 0.15 meter. Then our radial there, we know it's minus 20 megapascal. Then what about, what is this? That is simply, radial is simply A minus B over D squared. So This is what we know. Then radial there is minus 20 times 10 power of 6. Don't know the value of A and B. The diameter is 0.15. We square this will be simply equation 1. Then we go to next diameter. Say add diameter. What is that diameter? 200 millimeter. Same as 0.2 meter. So we know there the stress there will be what is 0. Here it's 0, isn't it? So the radial there is 0 megapascal. So what is this? We know this is equals to A minus B over D squared. Radial is 0. Here we have A minus B. We don't know. D is 0.2. We square. We make A the subject. Take that other side. Therefore, A simply equals to B over 0.2 squared. So this we have, isn't it, guys? So you can substitute, you can say here substitute. Can call this equation 2 into 1, where it's our 1. Here it's our 1. Isn't it? Let me grab it. Yeah, come here. Okay, we have minus 20 times 10 power of 6. Where I see A, I will replace with that. Know that A is equals to this, which is B over 0.2 squared minus this one, B over 0.15 squared. Then matter of maths, minus 20 times 10 power of 6. This is same as you take the common factor of B. We will be left with 1 over 0.2 squared minus 0.15 squared into, we have B. Take the common factor of B. Then we punch this on our calculator directly. If we punch that, say 1 over 0.2 squared minus 1 over 0.15 squared. Clips. This will simply, here we have minus here this side, like that. This will be negative 19,444. This will be B. Then we divide by this negative 19. This and this will cancel. Therefore, B will be equals to what? Simply I punch that minus 20 times 10 to the power of what? 6 divided by negative 19,444. Right. This is same as, all right, 1,029 times 10 to the power of what? 6. It's a value of B. Then the value of A, remember we have A here to be equals to this. So therefore A, when we see B, will have B will be 0.29 times 10 power 6 divided by 0.2 squared. Therefore A will be that 1,029 times 10 to the power of 6 divided by 0.2 squared. simply 25,725 times 10 to the power of what, 6. That is A. Now we find the hook stress at the outer. The hook stress at the outer. We said at the outer shaft. We want the hook stress at the outer shaft. Isn't it? And then that stress must be positive. Then that hook stress must be what they want. The maximum, or we find the maximum. The maximum, listen here, say the maximum hook stress at the outer. Maximum takes place where? At the smallest diameter is there. As you can see the graph, this will be maximum since it's still a common diameter is 150. Then hook stress there at again at 150. You know, hook stress is plus B over D squared. A is 25,725 times 10 to the power of 6 plus B, whereby B is 1,029 times 10 to the power of 6 divided by diameter 0,15 squared. Then what is the value that I will get? Let me punch this. 25,725 times 10 to the power of 9, okay, plus fraction of 1,029 times 10 to the power of what, positive 6 divided by 0,15 squared. Then oops, this will be what? It's a much bigger value. 25,77 0,733, yeah, times 10 to the power of 6, which is this will be simply megapascal. So yeah, we have this now. What else? The shrinkage allowance at the contact diameter. Okay, the shrinkage allowance, as we know, you see the shrinkage, right? Shrinkage allowance at the common diameter. Shrinkage allowance. The last question there. Shrinkage allowance at the common diameter. BDC common over Young's modulus into hook stress in the inner shaft must be inner minus the hook stress of the outer. So common diameter, we know that is 0,15. Yeah, Young's modulus of elasticity, what is that? Is 200. Okay, gigapascal. 200 times 10 power of what, 9. In the inner, hook stress in the inner is the one that, remember, in the common diameter we are checking, we have calculated that the hook stress, this is the outer one, this is the outer. Let's go to the outer shaft. We were talking about this is the outer shaft. Let's check inner shaft. This was the inner shaft. Let's check our hook stress. Here it's our hook stress. There. Here it's our hook stress here. As you can see, this is our hook stress. So this is simply okay. Let me put simply minus 3601.6 megapascal, isn't it, times 10 to the power of what, 6. We have minus here. Then the outer is this one we've just calculated here, which is surprisingly we got positive. Okay, there minus 25,770.733 megapascal times 10 power 6. Then let's see what we'll get there. All right, 0.15. Sorry about that alarm there. 200 times 10 to the power of 9 into negative 36 or 36,016 times 10 to the power of what, of 6 minus 25,770.733 times 10 to the power of 6. Then this into that. Then all right, this is shows that it's 0.0463, right? Or let me just write it like this, minus 46,34 times 10 to the power of minus 3 meter. This is the same as minus 46,34 times 10 to the minus 3 millimeter. Also, therefore, our shrinkage will be 46,34 times 10. Oh, remove this if we want that to be in millimeter. You see, if that I want that to be in millimeter, it's supposed to be like this, isn't it? Then the compressive shrinkage reduced, or this was shortened. The negative showing that it was shortened. Shrink. So yeah, this is what we have, guys. So thank you for watching, guys. Please do not forget to subscribe to my YouTube channel and click the notification bell so that you'll be notified whenever I post a new video. Please, by subscribing, you become a part of the family. You can support me by subscribing so that we grow together. All the best. Feel free to comment and share this to your fellow classmates. All the best.